This webinar tonight, which I call Leaning the Advanced Class, is a follow-up on the Leaning Basics webinar that we did a few months ago. Tim heads up, this is probably going to be a shorter than usual one, and so we'll probably have a little more time for Q&A than usual, which we always get a lot of Q&A when we talk about leaning. So, but there are just a few important points that I want to get across in tonight's webinar. And let me start off by doing a little review of some of the stuff we talked about in the Leaning Basics webinar. By the way, any of you who are at the advanced class but missed the Leaning Basics webinar, it is up on the EAA video server, and you can review it on your schedule. But anyway, I just want to review a few things about the mixture theory, and then we'll get into the main points of discussion tonight. And these next few slides are ones that were in the Leaning Basics webinar that I'm just going to use for review here. This is a graph showing the range of mixtures at which our spark ignition aircraft engines can run. The engine is capable of running across a very wide range of mixtures, ranging from 1 part fuel to 8 parts air on the rich side. These are ratios by weight, to 1 part air to 1 part fuel to 18 parts air on the lean side, which is obviously a very wide range. If we get leaner than 1 to 18, the engine flames out because the mixture is too lean to burn. And if we get richer than about 1 to 8, the engine quits because it's too rich to burn. We say it's a flooded engine. In this very wide range of mixtures, there are a number of particularly interesting ones. And I've noted them here with red stars. Starting on the rich side, which is the right side of the diagram, full rich mixture is what we use for start and takeoff. It's a very rich mixture. And as we lean the engine by pulling back the red knob, we get to a best power mixture, which is the mixture that gives the absolute maximum power output of the engine. And as we continue to lean, we get to a mixture called stoichiometric, which is the chemically perfect mixture, if you will. It's actually not a mixture that we normally ever use, except at very low power settings. But it's the fuel-air ratio where the amount of fuel and the amount of oxygen are as perfectly matched as possible, so that at the end of the combustion event, there is very little unburned fuel and very little unconsumed oxygen. And as we continue to lean, and the stoichiometric mixture is where we get peak EGT, so that's how we identify it, is with an EGT gauge. As we continue to lean onto the lean side of peak, we get to best economy mixture, at which we lose some power and a little bit of airspeed, but we make up for it by getting the best what's called brake-specific fuel consumption, the minimum brake-specific fuel consumption, which is basically you can think of it as the inverse of miles per gallon. So it's the best miles per gallon, if you will. It'd be best economy mixture. And then if we lean beyond best economy, the engine loses power very rapidly, starts running rough, and eventually will flame out. So again, these are the 4 interesting mixtures. Stoichiometric is the chemically perfect ratio. For various reasons, we don't use that mixture very often, but it is the mixture that we can identify easily because it is where EGT is maximum. So if we were to lean to peak EGT, we would be at stoichiometric mixture. If we go on the rich side of stoichiometric, about 75 to 100 rich at peak, we get best power mixture, which gives us about 3% more power about 1.5% more airspeed, because airspeed varies with the square root of power, but at a cost of about 20% more fuel. So best power mixture is not a very good deal in a world of $6 or $7 avgas, because we're throwing a lot of extra fuel in the engine to get a very, very small amount of extra airspeed. If we go onto the lean side of peak, we get to best economy mixture, which, depending on altitude and temperature and so on, will be somewhere in the range of 30 to 70 degrees on the lean side of peak. We lose about 10% of power at best economy mixture, which is only 5% of airspeed, but we do it with 20% less fuel than stoichiometric, or 40% less fuel than best power. So it's a very attractive mixture to operate at, unless you're a real speed demon and want to get that last couple of knots out of the airplane, because it gives us the best miles per gallon, the most efficient use of avgas. And then finally, there's full rich mixture, which is an incredibly rich mixture, typically 200, 250 degrees on the rich side of peak. Lots of excess fuel, gives us the same power as stoichiometric, but the reason that we use full rich for takeoff is to get increased detonation margin. Normally, the only times we would ever run an engine full rich are when we're starting it cold and on takeoff, and pretty much at all other times during the flight we will be leaning the mixture. Here is a graph again from the previous webinar of the key engine parameters showing how they vary with mixture. The curves are EGT, CHT, brake horsepower, and brake-specific fuel consumption, which is the measure of efficiency. In this particular graph, the x-axis, the horizontal axis, is fuel flow, with the low fuel flow or lean mixtures on the left side, high fuel flow or rich mixtures on the right side, and that dotted line down the middle is peak EGT or stoichiometric mixture. So you can see here best power mixture over on the right side, and you notice the lower star is at the peak point of the brake horsepower curve. This occurs 75 to 100 degrees rich of peak. Not a very efficient way to operate the engine, but if you need to get the very last little bit of horsepower out of it, that's the mixture you'd operate at. On the lean side of peak, we have best economy. That's where the brake-specific fuel consumption is minimum, and that occurs, as I said, 30 to 70 degrees lean of peak, depending on various factors. Stoichiometric, of course, occurs at peak EGT, best economy, best power we just looked at, and that mixture is which occurs at about 40 to 50 degrees rich of peak, is where cylinder head temperature is maximum and internal cylinder pressure is maximum. That is the most stressful mixture on the engine, and it's the place that we want to try to avoid unless we are operating at very low power. And again, the point of maximum CHT and maximum engine stress occurs about 40 to 50 degrees rich of peak. Interestingly enough, that's right where an awful lot of pilot operating handbooks recommend that you operate. Why? Because most of those pilot operating handbooks were written back before we knew about this stuff, and it turns out to be very bad advice. That's just about the worst place you can possibly operate the engine, at least in terms of longevity of cylinders and exhaust valves and stuff like that. And it's only an appropriate mixture if you're operating at very, very low power. Otherwise, we want to stay as far away from there as possible. So, moving on to the advanced stuff, the question that I always get asked is, what's the right way to lean my engine? And that's not the right question. And the reason it's not the right question is because there's no right way to lean your engine. There are lots of different ways to lean an engine, and some are appropriate sometimes and some are appropriate other times. A much more fruitful question to ask is, what's the wrong way to lean my engine? And that question has a very simple answer. Actually, I'm going to give it to you slightly simpler than it really is, and then refine it a little bit. But the simple answer is, the wrong way to lean your engine is to lean it in a way that allows cylinder head temperatures to get too high. And for the moment, I'm going to define too high as being above 400 degrees Fahrenheit. I will refine that a little bit as we go. But basically, cylinder head temperature is the closest proxy that we have in the cockpit to measuring stress on the engine. Cylinder head temperature varies directly with internal cylinder pressure, which is a measure of engine stress. And since we don't have an internal cylinder pressure gauge, the cylinder head temperature gauge is the best indication that we have of how badly we're stressing the engine. And I'm, for the moment, arbitrarily drawing a line at 400 degrees Fahrenheit and saying we never want CHT to be higher than 400 degrees. If we can keep it below 400 degrees, either by running very rich or running very lean or running low power, however you want to get the CHT below 400 degrees, then everything is good. And if the CHT is above 400 degrees, then that's bad. So we're using CHT as our primary reference for how we manage the power plant. And let me introduce a concept which was invented by my friend George Brawley, the chief engineer of General Aviation Modifications, Inc., who probably knows more about leaning and how to operate these engines than any man on the face of the earth. Among other things, George developed the world's most advanced aircraft engine test stand, located down in Ada, Oklahoma, and he has run engines for thousands of hours in that amazingly well-instrumented test stand, putting them through all sorts of torture tests, and has gathered more data on this subject than just about anybody in the world. And George originated the concept of the red box, which is a very simple concept. If we go back to a piece of that diagram we were looking at that plots EGT and CHT against mixture, George draws a line at 400 degrees Fahrenheit and says any mixture that causes CHT to be above 400 degrees is in the red box. We don't want to go there. And so this indicates, this one is drawn at 75% power, and it was based on an IO 550 engine, normally aspirated engine, it shows that in order to avoid being in this red box where CHT is above 400 and the pressures in internal cylinder pressures are abusive, we have two choices. We can either run quite rich of peak and get out of the red box on the left side, or we can run a little bit lean of peak and get out of the red box on the right side. Now, if this is at 75% power, if we were to lower the power to 65% power, the temperatures all come down and the red box narrows. Notice that the center of the red box is always right in that 40 to 50 rich of peak area, which is the most abusive mixture. And the red box is basically saying we want to stay away from that most abusive mixture, and how far we have to stay away from it depends on how much power we're running. So if we reduce to 65% power, the red box gets skinnier. If we reduced further to 60% power, the red box actually vanishes. So we've got this red box that we need to stay out of, whose width is a function of how much power we're running. High power, it's wide. Lower power, it's narrow. Low enough power, it actually disappears altogether. So the red box denotes the range of mixtures where cylinder head temperature is over 400 degrees Fahrenheit. We want to stay out of it. The lower the power setting we're running, the smaller the red box. If the power setting is low enough, the red box vanishes. Pretty simple concept. Now, let me refine this 400 degree number I've been talking about. 400 degrees is an appropriate maximum CHT for most legacy aircraft flying in most outside air temperatures. But if the temperature is very cold out, if it's below standard atmosphere, and most of the time we're at or above standard atmosphere, but if the temperature is cold, then we want to lower that 400 degree number appropriately. Also, if we're flying a modern designed aircraft like a Cirrus or a Diamond or a Corvallis that has an extraordinarily efficient engine cooling system, because some of the new design airplanes are much better in terms of engine baffling and so on, then we want to lower the temperature a little bit. So for example, my company manages a lot of Cirruses, and instead of the drop dead temperature being 400 degrees, we recommend for Cirruses that it be 380. And that would be true of other comparable aircraft that have very modern design engine cooling systems that are more efficient than usual. For the typical airplane, a Cessna 182 or a Bonanza or the Cessna 310 that I fly, or a Piper Cherokee or anything like that, the 400 is an appropriate value. But if the outside air temperature is very cold, or if the aircraft is a modern design that has a very, very efficient cooling system, we'll want to lower that number a bit. Now, another modification is that I don't want you to get the idea that anything below 400 is wonderful, anything above 400 is horrible. Of course, it's not quite as simple as that. It is a continuum. And so I've sort of modified the red box by putting a little yellow box around it, sort of a caution zone that we would sort of prefer to stay out of, and a purple box in the middle, which is an area that's highly abusive. And so, for the sake of argument, for a typical legacy aircraft at normal outside air temperatures, we'll say that the preferred limit is 380, the absolute limit is 400, and if you get to 420, that's a very, very abusive situation. Again, just a slight modification to the red box concept, just to emphasize the fact that 400 is not a magic number. It's just the higher above 400 you go, the more abusive you're being to the engine. The further below 400 you go, the kinder you're being to the engine, at least within reasonable limits. Now, I'm going to make a very, very controversial statement that will get a lot of people excited, but I'm going to explain why I'm saying it. I do not recommend using EGT as a leaning reference. We're talking about, best economy mixture is being 30, 50, 70 degrees lean a peak, and best power mixture is being 75 to 100 rich a peak. But I don't recommend that you use your EGT gauge to establish those values. And this goes against the conventional wisdom, but the reason that I think it's a bad idea to use EGT as a leaning reference, and why I do not do it myself, is simply this. If you use EGT as a leaning reference, the first thing you have to do is find peak EGT. And then you would adjust your mixture either on the rich side of peak or the lean side of peak. But the first step in leaning using EGT as a reference is to lean to peak EGT, which means very slowly leaning the mixture, watching EGT, and figuring out where it stops going up and starts going down. And the problem is that if you do that at anything other than a very low power setting, you are very slowly moving the engine right through the red box and right through the purple box. You're very slowly putting the engine right where you don't want it to be. So I don't think it's a very good idea to use EGT as a leaning reference. I prefer using techniques that just keep us out of the red box altogether, or if we have to transition through the red box, which we do when we're going from a richer peak mixture to leaner peak mixture, or vice versa, doing it as quickly as possible in a second or two, not dwelling there trying to fine-tune a mixture to figure out where peak EGT is. It's just an abusive procedure, and so I don't recommend doing it. Now I'm going to talk about a modification of the red box concept. It was invented by another friend of mine by the name of Gordon Feingold. And the red fin is something that looks like this. Again, along the bottom axis now is percent power that starts from a very high cruise power on the left, 85% power, and gradually works its way down towards 60%. And the red fin is the area where CHT exceeds 400 degrees, where we don't want to be. And the red fin sort of emphasizes the fact that the less power we run, the smaller the range of mixtures that get us into a high CHT situation that we're trying to avoid. So basically, the red fin is a whole bunch of red boxes just stacked up on one another. It's that simple. Now, if you think about the operating with the reference to the red fin, we have an area above the red fin, which is richer peak mixtures that we would normally use for takeoff, climb, and cruise. And then we have an area below the red fin that are leaner peak mixtures that we typically would use in economy cruise. If we go to very low power settings, then of course the red fin vanishes, and once we're below 60% power or so, there is no area that we need to keep out of, so we can set the mixture any place we want to. But in any case, this red fin indicates that we have basically two areas that we can operate in: one above the red fin, which is richer peak; one below the red fin, which is leaner peak. Now again, I'll modify the red fin a little bit by putting a little yellow caution zone on the outside of it and a purple zone on the inside of it. And again, the red fin is defined just like the red boxes were by reference to cylinder head temperature. The edge of the red fin represents the area where cylinder head temperature exceeds some threshold that we don't want to exceed. Now we get to the really interesting part. Let's walk through a flight from takeoff to landing and see how it works with reference to the red fin. And this is a very complicated chart, but just let me step you through it a bit at a time. We'll start with takeoff. We take off at basically 100% power, assuming the airport is close to sea level, and we take off with a full rich mixture, which in a typical airplane something like 250 degrees rich peak, very rich mixture. And then we start to climb. Now this particular discussion that I'm going to do assumes a normally aspirated airplane, not turbocharged, and assumes that the fuel system doesn't have any sort of automatic mixture compensation, so that the pilot actually has to do all of the mixture control themselves, and that represents probably the majority of the airplanes that you guys fly. If the airplane is turbocharged, or if it has an automatic mixture control or automatically compensating fuel system, then the procedure is easier because you don't have to fiddle with the red knob very much. But we'll assume a worst case condition, which is the most common condition, and that is a normally aspirated engine without any sort of automatic altitude compensation. So we start off at takeoff with a full rich mixture and which is a very rich mixture. There's something like 250 degrees rich at peak. And then as we climb, we should be gradually leaning the mixture because the mixture will automatically get richer and richer as we climb unless we do something about it. As you can see, the arrows kind of slope up, and then every 1,000 feet or 2,000 feet we pull back the red knob a little bit to keep the mixture in a reasonable place. Eventually we get to the top of climb, and at that point we decide that we want to transition from a rich of peak climb mixture to a lean of peak economy cruise mixture. To do that, we have to pass through the red fin, even through the purple fin a little bit, but the key is to do it very quickly. What George in his classes talks about is the big mixture pull, where we grab the red knob and briskly pull it back until we get to a comfortable lean of peak mixture, minimizing the time that we go through through the red fin and even the purple fin area where we really don't want to be because it's kind of abusive on the engine. If this is executed properly, it should only take 2 or 3 seconds to transition from a rich of peak mixture to a lean of peak mixture. And there are 2 ways to accomplish this. One is to simply pull the red knob back briskly until you start feeling a loss of power. When you start feeling a loss of power, that tells you you're on the lean side of peak. The other way to do it, after you've done it a few times, is to simply note the fuel flow where you're at a comfortable lean of peak mixture and just pull back the red knob quickly until you get to that fuel flow. But the key is that we want to do this quickly. We don't want to spend any more time in the red and purple fin areas than we absolutely have to. And that's why I recommend against using EGT as a mixture reference, because in order to establish peak EGT, we have to dwell right in the middle of that red fin area we don't want to be. So at any rate, now we're in a nice lean of peak cruise, and we cruise along until it's time to descend. When we start to descend, we typically just push the nose down, and then as the aircraft descends, if it's normally aspirated, the mixture will get leaner in the descent, and we have to compensate by pushing in the red knob from time to time until we complete our descent. So that is sort of the way we travel around this red fin. Again, the red fin is telling us where we don't want to be, and any mixture outside the red fin is an acceptable mixture. We want to stay out of it as much as we can, and if we have to pass through it, as we do when we transition from rich of peak to lean of peak, we want to transition through it just as quickly as possible to minimize the amount of time that the engine is in this abusive area. So just to review some of these things, we want to use the red fin as a conceptual tool to leaning. This is not a cookbook. I don't want you to print this out and try to duplicate it in the cockpit, because we aren't using EGT as a reference. We're simply trying to avoid excessive CHTs, and the red fin gives us a sort of a conceptual guide to the areas we have to avoid in order to avoid having excessive cylinder head temperatures. We want to avoid using EGT as a leaning reference because finding peak EGT, which is the first step in using EGT as a leaning reference, is something that is abusive to the engine, except at very low power settings, so it's best not to do it. We want to keep the CHTs below 400 degrees, below 380 if you can, to stay out of the red box or red fin area. If it's very cold out, or if your airplane has an unusually efficient cooling system, then you'll want to adjust that temperature down by 10 or 20 degrees. But the 400 and 380 numbers are good for most airplanes under most atmospheric conditions. And again, when transitioning through the red box or red fin, when you're going from Richa Peak to Lena Peak or the other way, we want to do it quickly. We don't want to spend any more time in the red area than we have to. So we just pull the red knob back briskly in 2 or 3 seconds. We can do it either by reference to the fuel flow gauge, or just lean to the onset of perceptible power loss. And once you feel a little power loss, you'll know that you're safely on the lean side of peak. And with that, you just graduated from the leaning advanced class. Now, if you want to learn even more about this, I heartily recommend the class that George Brawley and his associates put on from usually a couple times a year, called the Advanced Pilot Seminar. Their website is advancedpilot.com. It's not a cheap thing. They do a live version of the course, usually a couple of times a year in Ada, Oklahoma, and occasionally in other locations. It's a 2.5-day class, basically drinking from a fire hose, and the tuition is about $1,000. They also have an online version of the class, which is actually quite good for tuition of $400. But if you're a power plant management junkie and you want to learn a huge amount about this stuff, the Advanced Pilot Seminar is a very, very good one. It's a pretty major commitment, but if you want to get as smart as you possibly can on this subject, it's an excellent thing to do. And with that, Tim, I will throw it open to Q&A just to review our upcoming webinars that we'll be doing the first Wednesday of every month through the end of the year. And with that, let's do Q&A.
Awesome. Thanks, Mike. We've got some questions that have come in here, so let's just dive right into those. Oh, they keep coming in. Okay. Can you explain any detonation issues with running Lena Peak?
Yes. It is almost impossible for an engine to detonate when it's being run Lena Peak. The minimum detonation margin occurs at 40 to 50 degrees Richa Peak, right where a lot of POHs tell you to run, and where I'm telling you is absolutely the worst place to run. So if you want to avoid detonation, you either have to run quite rich, or you have to run Lena Peak. If you're running quite rich or you're running Lena Peak, it is almost impossible to get an engine to detonate. And I have spent hours in the test cell in Ada literally trying to put engines into detonation intentionally. And it's harder than you might think. But if you really want to do it, the place to start is to lean the mixture to about 50 Richa Peak, which is where the detonation margin is minimum. The notion that there's more risk of detonation with Lena Peak mixtures is just absolutely 100% wrong. As I said, the highest risk of detonation occurs at about 40 or 50 degrees on the rich side of peak, and which is right in the middle of the red box. And the further away you are from that that mixture, the more difficult it is for the engine to go into detonation. So if you stay out of the red box or stay out of the red fin, the stuff that we've been talking about, you're essentially guaranteed that the engine will not have any detonation issues. You know, unless you fill the tanks with Jet A or something like that.
Okay, we've had a few questions come in here about folks that are flying planes that don't have EGT or CHT. So do you have any tips for them to go through the leading process?
Well, I do, but I have to start off by saying that that I think it's very, very important to install an engine monitor with CHT and EGT instrumentation on every piston-powered aircraft. There is a mistaken notion that engine monitors are only really needed for high-performance, sophisticated aircraft, and that notion is exactly backwards, because it's the aircraft with the least redundancy that need good engine instrumentation the most. If I lose a cylinder on my 12-cylinder twin, I cage the engine and fly to my destination and think about how much it's going to cost to change that cylinder. If I lose a cylinder on a 6-cylinder Bonanza, I put the airplane down at the next airport and change my underwear. If I lose a cylinder on a 4-cylinder Lycoming powered Skyhawk or an experimental powered by a like 0320 or 0360 or something, that airplane may very well wind up on a road or in a field someplace. The less redundancy you have, the less cylinders you have, the more important it is to keep them running. And so I strongly recommend that anybody who is flying any piston-powered aircraft consider installing an engine monitor. Having said all that, I'll go back to the original question, which is, if you don't have decent engine instrumentation, how do you lean the engine? And the answer is, the best you can do is to operate full rich for takeoff and climb, and then when it comes time to go into cruise, lean the engine to the onset of perceptible engine roughness, to when the engine starts to get unhappy, and then enriching it just enough to make the roughness go away. In other words, the idea is to run right on the threshold of the engine running rough, and that will put you at roughly best economy mixture on the lean side of peak, which is a very, very good place to be. And without engine without engine instrumentation that lets you monitor CHTs and stuff, that's about the best you can do. And when I fly a Super Cub or something, that's how I fly it, because it's basically got no gauges in it, and it every year I go up to Michigan, and I have a weekend where we go fly Super Cubs and Aviation Huskies on floats, which is lots of fun. And those airplanes have basically no instruments whatsoever. In fact, one of them has a wet compass that says north no matter which direction you're going. And so it's pretty basic, and you just have to lean the engine by feel. You have to lean it to the onset of roughness. That's the best you can do.
All right, then we had a couple other questions in here coming about talking about determining horsepower while in flight.
Determining horsepower.
Yeah.
Well, again, there are two modes to operate an engine: rich at peak and lean at peak. When you're operating lean at peak, which is the way I normally operate my engine in all phases of flight other than takeoff and climb, computing horsepower is extremely simple. You take fuel flow and you multiply it by a fudge factor, and you get horsepower. For example, for a typical engine, normally aspirated engine that was certified for 100 low lead fuel, most of those have a compression ratio of about 8.5 to 1. The magic number is 14.9. If you take fuel flow in gallons per hour and you multiply it by 14.9, you get horsepower. for engines that have a 7.5 to 1 compression ratio, which is what most turbocharged engines have, and what some engines that were certified for like 91 octane have. The magic number is 13.7 horsepower. Gallons per hour times 13.7 gives you horsepower for those lower compression ratio engines. If the compression ratio is 7 to 1, which is about the lowest I think that we normally see in piston aircraft engines, those are engines that were certified originally to run on 80 octane, then the number's a little bit less. It's about 13 even. That only works lean of peak, because when you're operating lean of peak, power is proportional to fuel flow. When you're operating rich of peak, fuel flow no longer is the determinant of horsepower. The determinant of horsepower is mass airflow through the engine, which is obtained by multiplying manifold pressure times RPM. And so to calculate horsepower when you're running rich of peak, you really have to refer to the power charts in your POH, because there's no simple formula to calculate power when you're running rich of peak. When you're running lean of peak, it's very, very simple. It's just horsepower times a multiplier gives you, gallons per hour times a multiplier gives you a horsepower, and it's just very, very simple.
Okay. Cleon is.
I don't know if that answered the question, but that was.
I think it generally did. Yeah, there was. Yes, I think it generally did. There was a couple different questions worded a couple different ways that came in about that. So, Cleon is wondering, why would the limiting CHT be lowered for a modern, efficiently cooled engine? Doesn't the tensile strength of the cylinder material stay the same at 400 degrees Fahrenheit for a poorly and well-cooled engine?
Well, that's true if the only thing we were worrying about was the tensile strength of the cylinder head. That would be correct. But we're also concerned about the stresses on pistons and connecting rods and things like that that don't operate at cylinder head temperature. Internal cylinder pressure, which is really what we're trying to control, and we kind of wish we had an internal cylinder pressure gauge. If you go down to the test cell in Ada, they actually do have internal cylinder pressure gauges. They equip the engines in the test cell with special tricked out spark plugs that actually have pressure sensors built into them, which works great in the test cell, but those spark plugs are not certified, and the sensors are very expensive and they don't last very long, so it's not practical to put an internal pressure sensor in our production engines, or the engines that we fly around in. So it'd be really nice if we could. But in the absence of that, we sort of have to go by cylinder head temperature, and cylinder head temperature varies with internal cylinder pressure. But there are other things that affect it as well. Internal cylinder pressure is the most important thing that determines cylinder head temperature, but the volume of cooling air over the cylinder fins and the temperature of that air that passes over the cylinder fins also affect cylinder head temperature. So if we're trying to derive internal cylinder pressure from CHT, we have to fudge it a little bit, both when outside air temperature is very, very cold, and which would lower cylinder head temperature without reducing internal cylinder pressure, or when the cooling system is very efficient and more airflow over the cylinders occurs than normal. So that's why I'm saying in those two cases we really need to lower our cylinder head temperature targets a little bit to compensate for those things. I don't know if that was clear. It's a little bit complicated, but that's the essence of it.
Okay, Terry's wondering if a person can lean their engine, a turbocharged engine, using the TIT gauge.
Well, again, it's a bad idea to do that. we use a TIT gauge as a red line to protect the. By the way, for those of you who don't fly turbos, TIT means turbine inlet temperature, and it's another thermocouple probe, very similar to EGT probes, but just mounted in a different place. It's mounted very close to the where the exhaust gas first enters the turbocharger turbine section. And the purpose of the TIT gauge is to protect the turbocharger from being over-temped. If the turbine in the turbocharger gets too hot, the blades will start to stretch from centrifugal force, and eventually it'll start scraping on the turbine housing, and the turbocharger will have to get overhauled. So to protect the turbocharger, we set a red line, the turbine inlet temperature red line, which typically is either 1650 degrees or 1750 degrees, depending on what model turbocharger is used. But the only appropriate use for TIT is as a red line value to protect the turbocharger. It is not. It's not something that is a good idea to use as a leaning reference for exactly the same reason that EGT is not a good idea to use as a leaning reference, because again, to establish where peak TIT or peak EGT is, we have to dwell in that area that we really don't want to dwell in.
Okay, James asks, if there are big differences in CHT across the 6 cylinders of a carbureted engine, how does this affect leaning?
Well, first of all, in terms of red box and red fin, we want to keep all of the CHTs out of the red box, out of the red fin, so the one that will dominate our leaning decisions will be whichever one is the hottest. Now, if there are big differences between different cylinder head temperatures, there are 2 possible reasons for that. One is that the cooling airflow is uneven, and that's something that we should try to fix by making sure our baffles and baffle seals and intercylinder baffles and stuff are all in real good shape and are properly positioned and so on. The other reason is mixture imbalance, because carbureted engines naturally have a somewhat less consistent mixture between different cylinders than injected engines do. That's more so of certain carbureted engines. For example, the 0470 series engines that are used in Cessna 182s are notorious for having poor mixture distribution. The rear cylinders always run lean, and the front cylinders always run rich, and it's just an inherent part of the design of the engine's induction system. And on the other hand, Lycoming engines, carbureted Lycoming engines, and particularly sort of original design carbureted Lycoming engines, where the intake tubes pass through the oil sump, typically have much better mixture distribution, and normally the cylinders run pretty close to the same mixture. Some of the experimental Lycomings that have cold induction systems, that sort of screws up the mixture distribution, and I'm not sure the cold induction systems are a great idea that they use on some experimental versions of the Lycomings, because it does mess up the mixture distribution. If you do have a mixture imbalance, particularly if for example, if you're flying an engine like an 0470 that is notorious for having poor mixture distribution, there are 2 operational things that can usually help quite a bit to even up the mixture distribution in a carbureted engine. One is avoiding the use of wide open throttle. If you, for example, in a Cessna 182, if you were, say, cruising at 7,000 or 8,000 feet, where you'd normally cruise that airplane at wide open throttle, if you pull the throttle back just enough to get a slight decrease in manifold pressure, maybe a quarter of an inch, just a tiny bit, usually the mixture distribution gets a lot better. And it gets a lot better for two reasons. One is that pulling back the throttle a little bit closes off what's called the enrichment circuit in the carburetor, which is used to provide an extra rich mixture at wide open throttle for takeoff, but also screws up the mixture distribution. And the other reason is that by pulling the throttle back a little bit from wide open, you cock the throttle butterfly at a slight angle, and that generates turbulence as air is passing through the carburetor throat, and that turbulence helps mix the fuel with the air better and provide a better atomization and a more consistent mixture from one cylinder to the other. The second trick that helps, and particularly helps when in cold temperatures like during the winter, is to add a touch of partial carb heat, which again will cause the air going through the carburetor to be warmer and to atomize the fuel a little better. I have a lot of time in Cessna 182s, which, like I say, have probably the worst mixture distribution of any production engine, and using these two tricks, avoiding absolute wide open throttle and adding a touch of carb heat, can make a huge difference. And we do have a number of operators that are successfully flying Cessna 182s at least somewhat lean a peak, something that was traditionally thought to be impossible. But by using a couple of these tricks, you can improve the mixture distribution enough that you can actually run the engine a little bit lean a peak without it getting rough.
All right, Dan's wondering, so in the SR22, the Cirrus SR22, do you recommend to not use the lean assist function in the Avidyne glass panel?
I absolutely recommend against using the lean assist function. Again, that's an EGT-based function, and I do recommend not using it as a leaning reference.
Okay, George is wondering.
And again, it's not just Cirruses. I mean, a lot of airplanes flying around with JPI engine monitors that or Insight gems that have a lean find mode or whatever they call it. Different monitors call it different things. And again, I consider it to be a bad idea to use those features. I don't use them myself, and I teach my clients to avoid using those, again, because to use them you have to spend a lot of time in a place that's doesn't make the engine very happy.
Okay, George is wondering, isn't there a risk of leaning to the point of engine cutoff when you briskly lean?
No, I don't. I suppose I suppose it's possible, but I've been doing this for a long time, and it certainly never happened to me. Don't get carried away. But if you pull the red knob back in a a fairly brisk fashion, and you stop the moment you start feeling the engine losing power, that's right where the place you want to start lean a peak, and then you may want to fine tune a little bit from that point. But it will get you safely through the red box, the red fin, or whatever you want to call it, in the minimum length of time. You would have to pull it awfully far to make the engine quit, at least in my experience. It's not really a hazard. After you get used to it, and assuming you have some sort of fuel flow gauge, you can learn what a good target fuel flow is, and you can lean to that fuel flow. But just leaning to the point where you feel the engine start to lose power is a perfectly good way to do it. And no, I think the risk of leaning to the point of shutting the engine down is very, very small. I mean, I've never seen that happen.
Okay, John is wondering, is there a difference in monitoring CHT when using spark plug temperature probes versus cylinder well probes?
Yes, there is. And I generally recommend against using spark plug gasket probes, but if you have to use them, the spark plug gasket probes normally give you a CHT reading that's about 40 degrees Fahrenheit higher than what you would get with the standard probe that screws into the well. So if you are using spark plug gasket probes, and that's a good question, you need to increase all of those numbers, all of those CHT targets by about 40 degrees. I recommend not using those gasket probes unless you have to. There are certain engines where the cylinders actually don't have the normal threaded well on the bottom of the cylinder to screw in a CHT probe. Most engines do, and I would strongly recommend using the normal probe that screws into the bottom of the cylinder head as opposed to a spark plug gasket one. But if you do have to use spark plug gasket ones, you do have to adjust their values. It's typically about 40 degrees higher than what you would get with a standard CHT probe.
Okay, Ross says, in the Leaning Basics presentation, I think I remember you advocating on descent that the mixture not be adjusted. In this presentation, you are showing adjusting mixture on descent.
Well, I can understand the source of confusion because I went through a lot of stuff in the Leaning Basics presentation. The very last thing that I went through, the very last part of it, I talked specifically about how I manage the power plants in my airplane. And my airplane happens to be a turbocharged airplane, where the engine thinks it's at sea level no matter what altitude it's at. So in a turbocharged airplane, you don't have to lean the mixture as you climb, and you don't have to richen the mixture as you descend because it's automatic. There are also some normally aspirated engines that have altitude compensating fuel systems, and the same is true of them. Most normally aspirated engines do require you to lean as you climb and to enrichen as you descend, and that's the case that I was using in our trip around the red fin during this presentation. So I think that's where the confusion came in with that in the Leaning Basics presentation. The very last thing I did was to talk about how I lean my own airplane, and my own airplane is turbocharged, so the leaning is a lot simpler. A lot of stuff is automatic in a turbocharged engine that requires manual attention in a normally aspirated engine.
Oh, great. Yeah, we did have a few questions that come in about turbocharged engines, and just wondered if you want to make any additional comment on that to address those.
Yeah, well, go ahead and ask whatever questions there are. I'm happy to talk about it.
Just generally, what, for turbocharged engines, what do we want to look at for leaning?
Well, again, in a turbocharged engine, and there are various flavors of turbocharged engine too, but the typical turbocharged engine that has an automatically controlled wastegate, the leaning procedures are much simpler than they are with a normally aspirated engine. First of all takeoffs are made full rich, whether the takeoff is from Leadville, Colorado, or Jacksonville, Florida, because the engine always thinks it's at sea level, regardless of what the actual altitude is. And also, as you climb and descend in a turbocharged engine, you don't have to make any mixture adjustments, because again, the engine always thinks it's running at sea level, so it doesn't care what altitude you're at. So a turbocharged engine with an automatically controlled wastegate, which is what most turbocharged engines are, the leaning procedure is just a lot simpler. It's pretty much set it and forget it. Whereas in a normally aspirated airplane, where the engine is quite sensitive to altitude, because the mixtures are changing and the power is changing as you climb and as you descend, there's more pilot workload involved. And in in our trip around the red fin, I assumed that case, that we were dealing with a normally aspirated engine, because it's a more complex thing, and it's I think what probably the majority of people who are listening to this webinar fly normally aspirated airplanes, I would guess.
Mauricio is wondering, if I keep my CHT under 400 degrees, do I have a red box or red fin?
Well, I mean, if you keep it under 400 degrees, then you're staying out of the red box. Whether you have a red box or not depends on what your power setting is. But as long as you're keeping it below 400, which is sort of where we define the edge of the red box, then you're staying out of the red box, which is what you want to do. If you run enough power, there's always a red box, and if you run little enough power, there's always no red box. But if you simply keep the CHT target in mind, everything becomes very, very simple. You don't have to worry about anything except, is my CHT too high? If it's too high, you got to do something. If it's not too high, then you're good to go. I mean, that's why I really like using CHT as a leaning reference, because it's just so simple.
Great. Okay, John says, thanks for your thoughts. After attempting to run Lena Peak on my Barron's IO470L with GAMI injectors for years without success, will now gauge the Lena Peak with CHT.
Yeah, I'm curious why he didn't have success with it. The IO470 should be an engine that should run Lena Peak without problems if it has tuned injectors installed. But if he's having problems running Lena Peak, wants to drop me an email, I'll be happy to correspond with him about it.
Okay, here's a specific one from Douglas. What leaning technique can you suggest for a turbocharged B36TC Bonanza?
Well, gee, exactly, what we were talking about. Again, with a B36TC, the engine is very, very similar to the engines in my twin Cessna. They're TSIO 520s with an automatically controlled wastegate. And the specific leaning procedure that I use, which would be totally applicable to that Bonanza, is reviewed in the latter part of my Leaning Basics webinar, which you can get off on the EAA video server. That's would probably be the best starting point. But your airplane's engine is almost identical to the ones in my airplane, and so the leaning procedure would be pretty much identical.
Okay, Steve wonders, is there a way to estimate where peak EGT is without having to lean in order to find it?
Why would you want to do that? What's the objective?
He doesn't say.
Yeah, it's maybe he can ask the question again, but to me, the location of stoichiometric mixture is sort of a classroom exercise. Since we know it's not a mixture we want to operate at, why would we want to go to the trouble of finding it, particularly when the process of finding it puts us in an area we don't want to be?
Good question. Tom is wondering, how do we know that our engines are approved for Operation Lena Peak? He's got a Lycoming IO320.
Well, I mean, first of all, I don't have to be approved. The only things, the only operational things that we have to comply with are in the limitations section of the POH, and as far as I am aware, there aren't any POH limitations with regard to what mixture we can use. Interestingly enough, Lycoming has traditionally frowned on lean at peak operation until AirVenture 2011, when the chief engineer of Lycoming got up in front of a big group and said that Lycoming had changed its mind and it now felt that it was okay to operate Lycoming engines lean at peak. And we think that might have had something to do with the fact that Lycoming was in the process of developing a FADEC that was programmed to operate Lycoming engines lean at peak, so it would be a little embarrassing for them to say we don't approve operating engines lean at peak and then come out with a FADEC that did exactly that. But in any case, Lycoming's position in opposition to operating lean at peak was abandoned, at least if you can believe the chief engineer of Lycoming, a couple of years ago.
Great. Jerry says, I have a IO 360 200 horsepower with a 602 Insight EGT CHT.
Mm-hmm.
And it tells us to find peak EGT and then richen it by 25 to 50 degrees.
Right.
So are we lean at peak or rich at peak? Doesn't sound right, he says.
Well, if you do that, you're rich at peak, and not only are you rich at peak, but you're exactly in the area of maximum internal cylinder pressure, and you're dead center in the red box. You know, there are a lot of POHs, and there are a lot of I mean, the Insight manual that you're reading was written in the late 60s, back when we didn't know any better, back when people thought that was the best place to operate engines. We've now learned a tremendous amount, and it turns out that that all of the conventional wisdom that was floating around, originating, you know, back in the late 60s and early 70s, turns out to be very bad advice. And so, I mean, that's the reason I'm doing these webinars, and I write a lot of articles on this subject, and I'm doing a couple of talks at AirVenture this year, because it's time that we started abandoning this bad advice that we got from manufacturers that was originated years and years ago. I mean, the GEM 602 is an ancient device. It's and the manual for it was written back in the days when we were blissfully ignorant of what was really going on. We now know much more about what the best way and worst way to run these engines are, and that's kind of what this is all about. So anyway, don't follow the advice in your GEM manual for sure, because it'll put you right where you don't want to be.
All right, Michael says, I have been under the assumption that keeping cylinder head temperature below 380 degrees, regardless of power setting, altitude, and temperature. You have stated that temperature changes, ambient temperature changes that temperature limit. Can you elaborate on the relationship of ambient temperature and max CHT?
I can't elaborate on it a great deal because it's somewhat complex. The need to reduce the CHT target from 380 to something lower really only applies when it's really quite cold out. As I said, I wouldn't pay any attention to OAT unless it's below standard atmosphere, which is typically quite cool. It's not the kind of thing you'd ever have to worry about this time of year. It's something that you would probably have to worry about if you're in a cold climate like Wisconsin during the winter. If you live in the South, if you live in California where I live, it's probably nothing you'd ever have to even worry about. But if the weather is below standard atmosphere, then I would lower the target CHT by the amount that the OAT is below standard. And like I say, it's most of the time we're at standard atmosphere or above. Most of the time we're above standard atmosphere. So it's not something we have to worry about most of the time. But if it's particularly cold out, then it's worth worrying about. And you know, I fly a turbocharged airplane that, you know, I regularly fly up in the flight levels where, you know, the OAT might be, you know, -20, but it's still above standard atmosphere, so I don't have to worry about it. It's only if it's because standard atmospheric temperature is very cold up there. So it's only if the OAT is significantly below ISA, International Standard Atmospheric Temperature, that that you need to worry about adjusting the target temperatures downward.
Okay, Jim just says if you have any comment on keeping the throttle wide open during climb out and normal cruise on a high performance engine.
Well, as I talked about in my in the Leaning Basics webinar, in my airplane, which is a turbocharged airplane with a fairly modest manifold pressure red line of 32 inches. I push the throttles all the way forward on takeoff, and I never touch the throttles until it's time to land. They're wide open throttle for takeoff, climb, cruise, and descent. And if I could figure out a way to land the airplane full throttle, I would, but I haven't been able to figure that out, so I do retard the throttles for landing. But typically, I don't pull the throttles back before 5 minutes from landing. For the only time I would not run wide open throttle the whole flight would be in a highly boosted turbocharged engine, you know, something where you're getting 38 or 40 inches for takeoff. For a highly boosted turbocharged engine, you probably want to pull the throttle back a little bit, because carrying 38 or 40 inches for the whole flight is probably a bit much on the turbocharging system. For normally aspirated airplanes, I would run wide open throttle the entire flight for sure. And for turbo normalized or mildly turbocharged airplanes like mine, wide open throttle is fine for the entire flight.
Awesome. Okay, Dennis says, I typically lean to peak RPM in the climb, fixed pitch propeller.
Mm-hmm.
Is that a reasonable plan to stay out of the fin, or no?
Yeah, if you lean to maximum RPM, you're by definition leaning to best power mixture. Best power mixture is typically 75 to 100 degrees rich of peak, and is normally well above the red fin. So if you're leaning to maximum RPM, you're almost certainly in a nice safe area. Again, you know, if you have cylinder head temperature instrumentation, you should look at it. In a fixed pitch prop airplane, you're not required by regulation to have CHT instrumentation, although it's a really good idea to have it. But if you're operating at peak RPM, which by definition is best power mixture, you can be pretty confident that you're in a nice safe place on the rich side of, or on the rich side of peak and on the top side of the fin.
Okay, Bob is wondering, how accurate are CHT gauges and can they be trusted?
It depends. It depends on the gauge. It depends on the technology that the gauge uses. A lot of the digital engine monitors, like for example, the JPI system in my airplane, use thermocouples for measuring cylinder head temperature, and they tend to be extremely accurate. Other kinds of instruments will use thermistor gauges, which have a probe that varies in resistance by temperature rather than generating a voltage the way the thermocouple probe does. And the problem with thermistor probes is that because they vary resistance, they're very, very sensitive to anything in the system that would introduce spurious resistance, like connectors and that sort of thing that might introduce extra resistance into the circuit. Those tend to be a little less trustworthy. If you have a digital engine monitor that gives a digital readout, One thing that you can do is that before you start the engine, look at the cylinder head temperature digital readouts, and they should all agree, and they should all be at approximately ambient outside air temperature. You can't do that with a regular analog CHT gauge, because normally it's on the pin, it's on the peg until the cylinder head temperatures warm up. But if you have a digital gauge, you normally can read that temperature at whatever it is, and when the engine isn't running, before you start the engine, obviously all cylinder heads should be at ambient temperature, and so that's an easy way to do a quick check on the accuracy of the system.
Okay, great. Looks like something just came up on your screen there. Looks like
what is
Google,
that?
you got your Google Calendar up.
Oh, that reminds me I had this webinar, but it's in the wrong time zone or something. Okay. Well, I remembered it, so let's get rid of that. Sorry about that, guys.
All right, now we're back to your questions.
There you go.
Yeah, okay, so on with the questions here. Let's see here. Dan says, you said there is no detonation when lean a peak, but occasionally when too lean in a SR22, I experience these low-frequency sounds every 20 seconds, like backfires. What might they be?
Well, I can tell you almost exactly what they are. If you operate an SR22 significantly lean a peak, and you don't reduce the RPM, for those of you who don't fly Cirruses have a peculiar characteristic that they have a single lever, a single power lever that controls both the throttle and the propeller. And some Cirrus owners misinterpret the guidance to run wide open throttle as meaning running the power lever all the way forward, which not only gives you wide open throttle but also gives you 2,700 RPM. The engines aren't crazy about running lean at peak at 2,700 RPM. And I won't spend too much time on this because it's Cirrus specific, but the right way to operate the Cirrus in lean at peak cruise is to pull the power lever back until the RPM is under 2,500, then very slowly advance it back to the point where the RPM is exactly 2,500, and that will give you very close to a wide open throttle. In other words, the throttle body in the engine will be very close to being wide open, but the RPM will be at an RPM that's appropriate for running lean at peak. We don't want to run these engines lean at peak at RPMs higher than about 2,500. So I think if you keep your RPMs a little lower when you're cruising, you'll find that that popping noise that you're talking about won't happen anymore. If I'm wrong and it still happens, then I'd like you to dump your engine monitor data and upload it to our Savvy Analysis site, and then drop me an email, and I'll go take a look at it and see if I can figure out what your problem is.
Awesome. And let's see here. David says, is there a way I can calculate percent horsepower from RPM?
I take it this is in a fixed pitch prop engine.
He doesn't say. I would assume that.
Yeah,
I guess.
I don't know a way of calculating it. I think you have to use the power charts in the pilot operating handbook. As I said, the calculating horsepower when you're running rich at peak is quite complicated. Calculating when you're running lean at peak is very simple, and it's simply taking fuel flow and multiplying it by a factor. But if you're running on the rich side of peak, it's pretty complicated, and really the only practical way of determining power is to look it up in the POH performance charts.
Okay, Gary says, I was taught to lean during my run-up, then again as you climb, and finally when you level off. should you always take off at full rich?
You should, in a normally aspirated airplane, you should always take off at full rich unless you're taking off from a high density altitude airport where the density altitude is above 4,000 or 5,000 feet, and then it's appropriate to lean for takeoff. In a turbocharged airplane, you should take off full rich under all circumstances because, again, the engine doesn't know what the field elevation is, what the density altitude is. It always thinks it's at sea level. But normally aspirated engine, all takeoffs should be made with a full rich mixture unless the density altitude is quite high, say above, say 5,000 feet or so, in which case, of course, the engine is not producing full power. The problem is that when the engine is producing more than 75 or 80% power, which it normally is doing only during takeoff, that's when we are at the maximum risk of detonation, and to provide extra detonation margin, we run the engine full rich.
Okay. Robert says, based on what I've heard tonight, CHT gauges are more important for leaning. So, for what use would an EGT gauge be?
Again, my philosophy of using this stuff is that EGT is primarily useful in troubleshooting problems. First of all, detecting various kinds of engine anomalies, and then in troubleshooting those anomalies. It's not a good thing to use for operational control of the engine. Its primary benefit is in detecting and troubleshooting problems. For example, if a spark plug fouls in flight, the EGT on that cylinder will rise 50 to 75 degrees. And when you see that EGT rise, you know that you've got a non-firing spark plug. You can then do an in-flight mag check to figure out whether it's the top or bottom spark plug, and when you land, you can say to the mechanic, hey, change the bottom spark plug in cylinder number 3. That's the sort of thing that EGT is marvelous at, is diagnosing engine problems and pinpointing them. But it's not a very useful thing to be used in controlling the engine, leaning, and that sort of thing, because, as I've explained, using it that way is pretty abusive on the engine. And so I recommend not using EGT as a leaning reference, but I do recommend using EGT as a troubleshooting reference.
Gotcha. Okay, let's see here. Craig is asking, does spark plug condition have any impact on CHT? He says reference current issues with Champion spark plugs. And then also follow on, how about Magneto condition?
Okay, well, the condition of the spark plugs really doesn't have an effect on cylinder head temperature unless the condition of the spark plugs is so bad that it's causing some sort of very serious combustion anomaly. Like, for example, one of the problems that we've been having with the Champion fine wire spark plugs, and the reason we recommend against using them, is that they have a tendency to have their nose core insulators crack. And if the nose core insulator on the spark plug cracks, it can create a very serious situation called preignition. And preignition is something that causes cylinder head temperatures to go through the roof, to rise extremely rapidly, and to keep rising until something really bad happens, like the piston melts or something. But other than that sort of thing, that normal, say normally poor ignition condition, like the plugs are dirty or the gaps are too large or something like that, normally has very little effect on cylinder head temperature. With respect to magnetos, the one thing that has a profound effect on cylinder head temperature is magneto timing. So if the magnetos are inadvertently timed too far advanced, cylinder head temperature will be quite high. And if they're inadvertently timed too far in the retarded direction, cylinder head temperature will be low. Sort of interesting for those of you who fly Lycomings. Lycoming originally specified that all of their I guess IO360 engines be timed at 25 degrees before top dead center, which is a rather advanced ignition timing setting. And they had lots and lots of problems with high cylinder head temperatures. Lycoming is a company that has traditionally said, don't worry about high cylinder head temperatures, and they've set their CHT redline at an absurdly high value, 500 degrees Fahrenheit. But eventually, these high cylinder head temperatures were manifesting themselves in some detonation damage and so on. And so Lycoming suddenly decided that they were going to re-specify all of the timings on IO360s to be 20 degrees before top dead center instead of 25. And that dramatically lowered the cylinder head temperatures, dramatically reduced the incidence of detonation problems. And now there is a mixture of IO320s flying along. If they haven't been overhauled in a long time, they probably still have a data plate that calls for 25 degree timing, which is not good. And if they've been overhauled more recently, they've been retimed to 20 degrees. But mag timing has a profound effect on cylinder head temperature and on detonation margin. Pretty much nothing else in the ignition system has much effect on cylinder head temperature.
Great. I think that is a good note to wind up on, Mike. We've reached the end of our webinar tonight. It was an excellent session tonight, sir. Good question and answer with all the attendees. We apologize for the people who weren't able to get their question answered tonight.
Well, as usual, anybody who didn't get their question answered, please feel free to email me. It's my email address is on the screen, and I will do my very best to provide an answer to your question.
Thank you. Appreciate that. And you're going to be coming to AirVenture here. I guess it's about 3 weeks away now, and doing a number of forums. So anything you want to say about that?
I'm doing 11 forums. I think that's an all-time record. And most days of the show, there's one day that I'm only doing one, but the rest of the days I'm doing two, one in the afternoon, one in the morning, all on different subjects. And you can go on to the airventure.org website and do a search by presenter if you want to see what my presentations are and what day and time they're at. They're all in the same pavilion this year. They're all in the pavilion number 7, I think, which is the Honda pavilion. So
great.
Pretty much every morning and every afternoon. I think they're at 10 in the morning and 2:15 in the afternoon, most every day of the show.
Awesome. And then on August 7th, it looks like the next webinar you're going to be doing is titled The Redundancy Trap.
Yes, that's going to be tough because I'm only getting home from AirVenture on August 5th. So I guess August 6th I will soak my head in a bucket so I'm ready for the webinar on August 7th. That's a pretty tight.
That's a short turnaround, isn't it?
Yeah. If I have any airplane problems getting home, Tim, I'll have to tell you we may have to reschedule that webinar, but hopefully that won't happen, right?
I hope not. I hope you have good luck. I hope to see you while you're out here.
I maintain my own airplane, so if something goes wrong with it, it's whose fault it is.
Exactly. Yes, we know who to turn to.
That's right.
Well, Mike, thank you so much for tonight, and you have a great holiday tomorrow, 4th of July. To all the attendees, have a great holiday tomorrow, and looking forward to next week. We got on Tuesday, July 9th, Jim DiMatteo talking about EAA's AirVenture features and attractions for 2013. So thanks, everybody, and have a great night.
Thanks, everybody. Good night.